Here we are in section 1.4, looking at functions as mathematical models. So our objectives are to use a function as a mathematical model, determine whether a function is increasing, decreasing, or constant, and use the vertical line test to determine whether a graph represents a function. Okay. So in our first situation, we are looking at braking distance. So after an automobile accident, an investigating police officer is trying to estimate the speed of a vehicle by measuring its skid distance. They're using the skid distance to try to predict what the speed of the vehicle was. The following table gives an average for skid distances for automobiles with good tires on dry pavement. Does the table define speed as a function of skid distance? So we can scan through our values for distance to make sure that each of the values has just one output. There are no values in our input column that are repeated, so we can answer yes here because each input, each distance, skid distance, which is our input, corresponds with exactly one output. With exactly one speed, which is the output. Identify the independent variable and the dependent variable. So the independent variable in this case is our skid distance. And the dependent variable in this case is our speed, since we are using skid distance to predict the speed. Plot the input-output ordered pairs and label. Now that we've done some graphing with technology, we're going to do all the rest of our graphs versus technology. So we're going to graph this on decimals. If we want, we can do a quick plot on the paper after we've done so. But it makes more sense to get our tables going this way. All right, so we're going to create a table and enter our values. So I'm going to enter all my inputs first. Let me actually move this up to the top. Put my book down a little bit. Enter all of our inputs, then I'll come back and I'll enter all of my outputs. I just find that doing all of the inputs first is easier because I can hit enter in between them instead of having to like tab over. I don't know. Just makes it nicer for me to type. So I typed in my two columns and then I'm going to zoom fit with the button at the bottom of the table so I can see the data. All right, so I'm going to make a quick sketch of what I observe. So it's kind of got a curvy shape. So when I drop my dots in, it's not quite straight. So I'm going to plot them like that. I didn't. All right, so it's kind of like that curving shape going up a little bit. All right. And then as we can see, of course, the axis gets us at 400 on the x-axis over here at the edge and only 100 up there. So I'll label my top here at 100, bottom at 0, and then 400 over on the other side, which again, you can, if I push the page down, you can see my 400 on the far side. Okay, move decimals out of the way. After an accident, the skid distance was measured to be 200 feet. From the table, the investigating officer knows that the speed of the vehicle was between 65 and 70. That's because, let me pull the table back over here for a second. Oops, I grabbed the wrong window. There we go. That's because the input 200 is in between these two inputs. So the output must be between 65 and 70. That's what the officer is concluding. She would, however, like to be more precise. So one way of getting values that are not listed in the table is to use an equation that best fits the data. And that equation that best fits the data is going to be called our mathematical model. So that's what we're going to be looking for here is a mathematical model. It is an equation or graph that fits approximate or approximates the actual values. So it approximates actual values, and the model can be used to predict output values for input values not in the table or in the table, any input values in or out of the table. Okay, so they have given us an equation here. Let me push that so I can see the equation and I can type it in down here. They're saying it's not really a specific curve or a line, but I can guess that this function f of x equals negative 0.00029x squared plus 0.31x plus 18.6. So like, does that kind of fit? So later on, we're actually going to be working on how to get that equation. Right now, we were given this equation with these rounded coefficients, and we're kind of just asked, like, does it fit? So back to my book for just a second. Look at this. It says, like, graph it. There's some weird calculator windows. All I got to do to graph it is to type the function as I have done. So f of x equals, type my function into Desmos. Then there is some issue of rescaling the window. Now, mine is already rescaled based on the table. But if I wanted to rescale to match their window, I can see that the x-min that they have chosen for me is 0. The x-max that they have chosen is 450. So even though that they have given me this information in the table, they've got a step of 50. I can put the 50 in. It just rescales the x-axis in terms of what's labeled. And then on the y-axis, the minimum is 0, the maximum is 100, and they've stepped it by 10. So you can see that when I put that step size in, just change the labels. So the Zoom Fit got me something similar to this, but if they ever give you one of these little boxes, they're giving you the information that you need to type into the graph settings, just displayed in a different way, displayed for those calculators, but we can still organize our information with the 3 things that we need to know for x and the 3 things that we need to know for y: the minimum value, the maximum value, and the scale for both x and y. Okay, the rest of the stuff doesn't even matter on the calculator. Like the delta x and the trace step don't matter at all. For Desmos doesn't have a trace step. It will allow you to trace, click and drag and trace without regard to any specific step. So that's not something that matters in terms of Desmos. Okay, so they asked us to rescale our graph. So done. And they asked us to graph. Calculators are so complicated. There's so many buttons to push. But the graph is already in our Desmos window, and we've rescaled it. And so let's continue over onto the next page. So what they would like us to do now is use the graph to find out. I'll move Desmos off for just a second so we can see the question. Use the graph to find out when exactly the distance is going to be 200 feet. Now they're asking me to use trace, okay? So there's no specific way to use trace, but we're just going to click and drag for trace. Okay, not actually the best way. We'll talk about a better way in a moment, but first click and drag for trace. So 200, I can see that 200 is about here, so I'm going to start my click here, and I'm just going to hold my mouse, try to get it to land right on 200. There we go. So hey, I got about 69, and again, when my hand moves a tiny bit, it moves. So there we go, 269. I have to hold my hand really still so it doesn't move on to another point. But I can see that the car must have been going at about 69 miles per hour. Okay, so trace is a little finicky. You have to be really careful when you're clicking and dragging. And if you're using a touch screen instead of a mouse, it's actually a lot harder to use trace. So trace is one way to get you ballpark information, but it's much easier to just call the function f of 200. Plug the number that you want to plug into the function into the function. And so you can see that you get 69. So the other way to do it is to evaluate I'm going to even note in front of this f of 200, because all you got to do is type f of 200 and it gives you that 69. So 200 comma 69 came out as our ordered pair, and when we plug in 200 we get 69 as well. All right, one more way. This is their function evaluation way. This would have been just typing it by hand manually. Like technically I could have retyped this entire equation, although again it doesn't make I was trying to copy undo. Doesn't make a ton of sense to do that when I can just use function notation, but I could have retyped all these little numbers manually. Hopefully you'll soon realize that this is not like the best way to do this, because it takes a whole bunch of extra time. And again, you get 69. It's a lot easier to call the function. So that's what they are doing here last. So this second one technically is retyping the function, and then this third one is our evaluation of f of 200. That's the best way, is the f of 200, fastest way. There's a third way though. So our fourth way. Since 200 is an input value, an x value, if you graph x equals 200, it'll pop a vertical line at that position. Then you can click on the intersection. So it's kind of like using the trace, but you can actually click right on the point because you have 200 marked off, and so you don't have to worry about wiggling back and forth. So as a method number 4 that we'll just mention, the calculators don't do this very well, so they didn't mention it here. But another way, so method 4, is you can graph x equals 200, and then you can click on that point of 200, 69. So many different ways we have right here of answering the question, what speed was the vehicle going if it had its skid distance of 200? It was going at 69 miles per hour. Okay. Now that we answered that question, we're going to look at definitions of increasing and decreasing functions. So first of all, a function is increasing if it is going up to the right, like this. Sorry, my book does not quite fit here. It's increasing if it's going up to the right, and it is decreasing if it's going down to the right, so like this. And last, it is constant if it is horizontal. So constant if it is horizontal, so flat. Okay. Now, in each case, you're viewing a graph that moves from left to right, so as the input values increase. So increasing, decreasing, constant. So is this function increasing, decreasing, or constant over the domain displayed in the window? So it's increasing, right? It's not increasing in a straight line pattern, it's increasing in a curved, but it's going up the whole time in this window. So it is increasing. Move decimals out of the way before I write. It is increasing in this window. And the picture looked something like this, or it was that curve that was going up, a little taller than that. I didn't have room to draw everything, but it was increasing from left to right for sure in that window. Okay, so to cover our weekly expenses while going to college, we're in $100 as a part-time job, and the following table represents our pay for a typical month, or our expenses, I should say, for a typical month. Plot the data. All right. So, starting off here, we have our salary as 100, and our weekly expenses are 100. So I'm going to say 100 is right there. Okay. And then my weekly expenses, let's say those are, need to get up to 90. So 25 every other one, and say 50, 75, and 100. Okay. So weekly salary. So I'm making $100. So in the first week, my expenses are 50. In the second week, my expenses are I still make $100, but my expenses are 70. In the third week, my expenses are 90. And in the 4th week, my expenses are 60. So are the weekly expenses a function? Oh my gosh, I'm so sorry. Let me just tip my camera so that I can see the bottom half of my page a little better. I'm looking at my book, and so I'm not necessarily noticing, and I can't see it on my screen. So when I graphed these, we're graphing at 100, and that was the input, that was the salary each time. But the expense, the output, changed. I plotted the 50, then the 70, then the 90, then the 60. Are weekly expenses a function? We're going to have to say no, because the input didn't change, and the same input had a whole bunch of outputs. Okay, so the same input, specifically 100, has more than one or multiple possible outputs. Okay, on to our next page. Do all 4 points lie on the same straight line? Well, yes. And is that line horizontal, vertical, or slanted? It was vertical. How can you determine from the graph that it does not represent a function? More than one point lies on the same vertical line. Because that single x value had multiple outputs. So if any 2 points lie on the same vertical line, it's automatically not a function because you have an input value that has multiple outputs. Okay. Notice that all the input values lie on the same vertical line. Yes, a vertical line can be thought of as the graphical representation of the input value. Yes. So draw a line whose points all have an input value of 2. So I'm going to draw x and y axes first. And I want to draw a line such that they all have an input value of 2. So 1, 2. That would be where 2 is right there. That would be where 1 is. And same thing on the next one. Let me draw in x and y axes. Draw a line where the input value is -3. So -1, -2, -3. These all have an input value of -3. Just for fun, the equation of this vertical line would be x equals 2, and the equation of this vertical line would be x equals -3. Remember, the input is x, so if the input's going to be 2, it's x equals 2, and the input is -3, it's x equals -3. Okay, number 9 says that a unit circle is a circle having a center at the origin and a radius of 1. So such circles are commonly used in trig. This is a graph of the unit circle. Does this graph represent a function? Explain how we can determine if it represents a function. It's not a function because there are points that fall on the same vertical line. Okay, if I drew, I could draw it anywhere. I just happened to draw that one. I could have drawn it anywhere else, but it's going to be no, and it's going to be no because there are some inputs with multiple outputs. Just has to happen once. If it happens more than once, that's fine too, but it's certainly not a function because there are some inputs with multiple outputs. So from the graph, you can use the vertical line test, which means if you draw a vertical line and it crosses the graph at more than one place, then that's a visual demonstration of some inputs having multiple outputs. So this graph right here fails the vertical line test, therefore it is not a function. Okay, so this one fails the VLT, which is the abbreviation for vertical line test, fails the vertical line test because the vertical line hits in more than one place. And that means it's not a function. Not a function. There we go. Last questions over here on the next page with number 11 and 12. Use a vertical line test to determine which of the following represents a function. So if I drew any vertical line at any point here, they only touch the graph one single point. So no matter where the vertical line is, it only touches one point. So this passes the vertical line test. So that means it is a function. But over here, I could draw a bunch of vertical lines, but this one in particular would hit the function twice. So it fails. It doesn't matter where you draw, if you drew it over here or wherever. If you can draw any vertical line that hits it more than once, it's going to fail the vertical line test, and it's going to not be a function. If a graph is increasing everywhere, does the graph represent a function? So if I'm increasing everywhere, no matter if I have like little curves or dips, I never turn in decrease, I'm always increasing, then there's no opportunity for this function to turn around and fail the vertical line test. So yes, because each input must have an output that is higher, aka not equal to, the input previous. Not that being equal to would be a problem, because constant functions are still functions, but there's never an opportunity for one input to have more than one output. So we're going to have to add on to that by saying each input has a unique output. Has one specific unique output. That's what unique means, but spelling it out. One unique output, and that is why it is a function. All right, and we've reached a summary.